A volcano nobody had been watching for 54 years just woke up beneath the Pacific Ocean. The eruption is happening 1,300 meters below the surface, north of Papua New Guinea. The ash column is reaching 9,000 feet. The earthquake swarm that opened the vent is still rolling. And in the same volcanic arc, in 1888, a flank collapse from a comparable volcano killed several hundred people and sent 50-foot waves across hundreds of kilometers of coastline. You are about to find out why the tsunami risk in the Western Pacific is now climbing and why you should be paying close attention. Let's get into it. On the 8th of May, in the central Bismarck Sea, north of Papua New Guinea, a submarine volcano that has not erupted in 54 years began erupting again. The eruption is happening 1,300 meters below the surface of the ocean. That is about 4,300 feet of seawater between the vent and the sky. And despite that pressure regime, the vent is producing an ash column that is breaking the surface and climbing 9,000 feet into the atmosphere. The plume has been visible on geostationary satellite imagery for multiple days. The Darwin Volcanic Ash Advisory Center has issued an ongoing advisory for the affected airspace. The ash is spreading tens of kilometers across the central Bismarck Sea, and the volcano producing it has only ever been observed in eruption once before, in January of 1972. This is the second eruption in recorded history of the central Bismarck Sea volcano. That is a fact worth holding on to. Not because the volcano is famous, the opposite. This is one of the most obscure submarine volcanic systems on the planet. It does not have a proper name. It does not appear on the major volcano monitoring program watch lists. Its bathymetry has never been mapped at modern resolution. The reason we even know it exists is that in 1972, hydroacoustic stations registered an unusual acoustic signature that was traced to a fissure ridge in the central Bismarck Sea, and the system was added to the global catalog with a coordinate and a footnote. After that, it went quiet. For 54 years, almost nobody monitored it. Nobody followed up. And then, on the 8th of May, 2026, it came back. The eruption began with an earthquake, a magnitude 5.6 earthquake at 12:22 Universal Time on the 8th of May. The Global Seismic Network registered it as a single sharp event, depth assigned to 10 kilometers by default, because the local instrumentation in the central Bismarck Sea is not dense enough to calculate a real depth. A magnitude 5.6 is not, by itself, a remarkable earthquake. What makes this one different is what it was. This was not a clean strike on a continental fault. This was not subduction stress releasing between two converging plates. This was a magma intrusion. The seismic signature, the location relative to the volcanic ridge beneath the Bismarck Sea, and the timing of what followed all point to the same thing. The earthquake was not the event. The earthquake was the door opening. The event is what came through it. This is what is happening right now. The eruption is sustained. The seismic activity is continuing. The Pacific Tsunami Warning Center has not issued a warning. Coastal tide gauges have not registered an unusual wave. The most likely outcome over the next several weeks is that the eruption tapers and the system returns to dormancy. The least likely outcome is something on the scale of what happened in this exact volcanic arc in 1888, when an island called Ritter collapsed into the sea and killed several hundred people on coastlines 600 kilometers in every direction. The probability of the worst case is low. The conditions that would precede it are present. That is what this video is about. The earthquake swarm that opened the vent on the 8th of May consisted of several cataloged events. The magnitude 5.6 main shock at 12:22 Universal Time, a magnitude 5.0 follow-on event later the same day. Multiple magnitude 4 class aftershocks. The most recently cataloged event in the immediate sequence occurred on the 9th of May at approximately 0900 Universal Time. Magnitude approximately 5. All assigned 10 kilometers depth by default. None of these are spectacular numbers on their own. Earthquakes of this size happen somewhere on the planet every day. What matters is where they happened and what they triggered. The catalog only captures the largest events. The global seismic network reliably picks up earthquakes down to about magnitude 4.5. Below that, in remote regions like the central Bismarck Sea, smaller events are not consistently recorded. There is no local network of seismographs in this part of the Western Pacific. There are no permanent ocean bottom sensors near the eruption site. So the cataloged events are the tip of the swarm, not the swarm itself. The actual seismic activity over the past 5 days is much greater than what shows up in the public earthquake feeds. The spatial pattern of the swarm is also important. The cataloged events are not concentrated at a single point. They are spread across an area approximately 12 to 15 kilometers across at the inner cluster, with some events appearing as far as 30 kilometers from the primary vent. That is not the signature of a single vent volcano producing aftershocks. That is the signature of a larger volcanic field or fissure system feeding the active eruption. The earthquake pattern is tracing out a volcanic ridge. The ridge is poorly mapped. The bathymetric data we have on it is marginal. But what it shows is consistent with a system that hosts multiple potential eruptive centers along its length. The active vent producing the ash plume right now may be the most active point along the ridge. It is almost certainly not the only point capable of producing eruption. The timing tells us something too. The magnitude 5.6 main shock was at 12:22 universal time on the 8th of May. The first satellite imagery showing a developing ash plume came about 8 hours later. 8 hours is not a long time in geology. What that timing tells us is that the magma intrusion was massive enough and pressurized enough to crack the overlying rock and open a vent to the surface within hours. This was not a slow buildup with weeks of precursor activity. This was a sudden injection of fresh magma that punched through the lithology above it and started erupting almost immediately. That kind of transition is not impossible. Submarine volcanic systems with deep magma supply can transition from quiescent to actively erupting on timescales that the surface volcano playbook does not prepare you for. And right now, that is what the central Bismarck Sea is doing. Here's the part that, by every conventional measure of submarine volcanism, should not be happening at the scale we are watching. The eruption is sending an ash plume through nearly a mile of seawater, and then up 9,000 feet into the atmosphere. The vent is at 1,300 meters depth. The hydrostatic pressure at that depth is approximately 130 atmospheres, 1,915 pounds per square inch. That is the weight of a mile of seawater bearing down on every gram of magma at the vent. Under normal submarine eruption conditions at that depth, that pressure regime suppresses explosive volcanism almost completely. Magma erupting at 1,300 meters typically does one of two things. It either extrudes slowly as pillow lavas, where the surface of the magma freezes into glass the instant it contacts seawater, or it fragments into a relatively quiet column of steam and ash that struggles to make it to the surface. What does not happen, typically, at 1,300 meters is a sustained ash plume that breaks the surface and reaches 9,000 feet of atmospheric altitude. That is what is happening at the central Bismarck Sea right now. That is not a typical submarine eruption. That is something that requires explanation. The explanation almost certainly involves three things operating at the same time. The first is a volatile rich magma. The chemistry of what is being injected has to be unusually gas-rich for the eruption to maintain explosive character against the overlying pressure. The second is steam generation. Contact between magma at roughly 1,000 degrees Celsius and seawater at near freezing temperatures produces violent flash boiling, and the volume expansion of that steam against the water column generates buoyant convective columns that can rise rapidly through the water. The third is pumice rafts. Magma fragmenting at depth in a volatile rich eruption produces enormous quantities of pumice, which has a density lower than seawater and floats. Pumice rafts can carry trapped gas to the surface and release it to the atmosphere, scattering ash into the wind. The combination of all three mechanisms is what allows a vent under a mile of water to feed an atmospheric plume. The operational reality of all this is that the system has access to the energy budget and the volatile content required to maintain an atmospherically visible plume against extraordinary pressure. That does not mean the eruption is going to escalate. Most submarine eruptions of comparable early phase character do not escalate. They proceed at roughly their current scale until the magma supply is depleted, and then they fade. But the fact that the plume exists at all, at the scale and persistence we are seeing, tells us the system is at the upper end of what submarine arc volcanism can do. Before the 8th of May, the central Bismarck Sea volcano was on no list anyone was actually checking. It had not been monitored, it had not been mapped at modern resolution, it had not been studied. The reason for that obscurity is that the volcano has only ever been observed in eruption once before, in January of 1972. That eruption is also how we discovered the volcano in the first place. The story of the 1972 discovery is itself a story about how much we do not know about the seafloor. In early January of that year, hydroacoustic monitoring stations registered an unusual acoustic signature emanating from a region of the central Bismarck Sea. The signal did not match a submarine earthquake. It did not match a nuclear test. It was longer, lower in frequency, and it persisted in repeated bursts over 4 or 5 days, from January 8th through January 12th. Triangulation from multiple stations narrowed the source to a region where no volcano had been mapped. Follow-up ship-based surveys identified a fissure ridge rising from the deep abyss, and the eruption was attributed to that system. That was it. The eruption tapered. The signal faded. The volcano was added to the global catalog, and for the next 54 years, almost nobody followed up. 54 years is, by submarine volcanism standards, a short dormancy. Many submarine arc systems have intervals between eruptions measured in centuries. What is unusual is not the dormancy itself. What is unusual is the abruptness of the return. The volcano did not give us decades of escalating unrest. It did not bulge. It did not vent gas. It did not produce a slow buildup of microseismicity that anyone was tracking. It went from silence to a magnitude 5.6 magma injection earthquake, and then from that earthquake to a sustained eruption with an atmospherically visible ash plume in a window of hours. That is the kind of transition that should remind everyone watching that the dormancy of a volcano is not a guarantee of how it will behave when it returns. A 54-year quiet is not a 54-year warning. It is a 54-year absence of warning until the system decides otherwise. There is one more piece of context that matters. The volcano has only ever been observed in eruption from the surface twice. Once by acoustic detection in 1972, once by satellite imagery this week. There has never been a direct visual observation by a research vessel of the active vent. There has never been a deep submersible deployment. There has never been a survey during eruptive activity that could characterize the vent geometry, the magma chemistry, or the eruptive style with any precision. What we know about how this volcano erupts, we know by inference from analog systems. That is a profound informational gap. And it is the gap that makes everything that comes next, the question of escalation, the question of flank collapse risk, an exercise in working with the analogs we have rather than the data we wish we had. To understand why everyone paying attention to the central Bismarck Sea is talking about tsunami risk, you have to go back to March of 1888, and you have to look at what happened approximately 200 kilometers south of where the current eruption is, on an island called Ritter in the southern Bismarck volcanic arc. In the pre-dawn hours of March 13th, 1888, Ritter Island ceased to exist as a structure. Half of the island gone in minutes. Approximately 4.6 cubic kilometers of rock and ash and crystallized lava detached from the volcanic edifice as a coherent debris mass, sliding into the sea at speeds estimated at 40 meters per second or greater. 40 meters per second is about 90 miles per hour. The mass entering the water displaced enormous volumes of ocean and generated tsunamis that radiated outward from the collapse site. The run-ups documented from the 1888 event are staggering. Trees were stripped from the lower slopes of the adjacent islands of Umboy, Sakar, and the western shores of New Britain at heights of approximately 15 meters above sea level, which is the diagnostic feature researchers use to estimate the actual peak run-up. Because trees can withstand partial overtopping, up to a fraction of their height, the actual peak run-up is interpreted to have been in excess of 15 meters, with literature estimates in the range of 20 to 50 meters at certain locations. 50 meters is 160 feet. That is the height of water that overran the coastlines closest to Ritter on the morning of March 13th, 1888. Several hundred people died on those coastlines. Significant damage was documented at distances up to 600 kilometers from the source. The Ritter event was not an outlier in this volcanic arc. A 2008 paper in the Journal of Volcanology and Geothermal Research by a research team that included Silver, Watts, and Day used side-scan sonar and high-resolution bathymetry to identify 12 distinct flank collapse debris fans across the Bismarck Arc. 12 documented mass failure events with individual fan footprints ranging from 20 to 150 square kilometers. 12 mass failure events across approximately 50,000 years of arc history implies an average return interval across the entire arc of about 4,000 years per location for events large enough to leave detectable bathymetric signatures. 4,000 years per location sounds like a long time, but on a volcanic system timescale, it is short. The Bismarck Arc produces flank collapse as a recurring feature of its evolution, not as a rare anomaly. The current eruption is in the same arc system. The structural conditions that elevate flank collapse risk right now are present. The eruption is sustained. The earthquake swarm is continuing to stress the volcanic edifice. The ridge geometry is poorly mapped but appears to extend across distances, suggesting multi-vent geometry. There are also some differences between Ritter and the central Bismarck Sea that bear directly on the magnitude of any potential downstream event. Ritter was an aerial volcano. Its mass was above the waterline. The central Bismarck Sea volcano is fully submarine. Its edifice is under 1,300 meters of water. The hydrostatic damping effect of that overlying water column reduces, but does not eliminate, the amplitude of any tsunami that a comparable collapse would generate. The empirical landslide tsunami framework indicates that for a fixed slide volume, doubling water depth at the source roughly halves the peak run-up. A comparable volume collapse at the central Bismarck Sea Ridge at 1,300 meters depth would therefore produce run-ups on the order of 8 to 25 meters at adjacent coastlines. Still catastrophic. 8 to 25 meters of water arriving at a coastline is the kind of event that kills people and destroys infrastructure across kilometers of shoreline. It is just not the 50-meter Ritter scale. The qualitative point is what matters. The Bismarck Arc has produced one mass casualty flank collapse tsunami in the historical record, and the conditions that produce that event are present in modified form at the central Bismarck Sea right now. There is one more historical event from this region that matters, because it directly explains why the current tsunami risk is operationally serious, despite the warning system being silent. On the afternoon of July 17, 1998, on the northern coast of Papua New Guinea, near a town called Tape, the ocean retreated from the shore. The water pulled back several hundred meters. Within minutes, the water came back as 3 successive waves, the largest of them estimated at more than 10 meters tall, breaking across the coastal villages of Sisano, Warapu, Arup, and Malo. More than 1,600 people died in those few minutes. The trigger for the Etape tsunami was an earthquake, a magnitude 7.0 event, a few kilometers offshore. A magnitude 7 is significant, but the magnitude 7 at Etape was not the kind of thrust event that conventionally produces a large tsunami. The conventional model applied to that magnitude 7 would have predicted a tsunami of perhaps 1 to 2 meters at the coast. What arrived was more than 10 meters. The reason for the discrepancy is what makes Etape directly relevant to what we are watching right now. The actual tsunami at Etape was not generated by the earthquake itself. It was generated by a submarine landslide that the earthquake triggered. The continental slope offshore of Atape had accumulated unstable sediment over thousands of years, and the magnitude 7 was enough to push the slope past its failure threshold. The momentum transfer from that slide into the surrounding ocean generated the destructive waves. The earthquake was the trigger. The landslide was the mechanism. That distinction matters because the conventional tsunami warning system relies on detecting large earthquake signatures to issue regional warnings. It did not warn for Itape because the earthquake itself was not the kind of event the system flags as a major tsunami source. The warning architecture issued only a localized advisory after the wave was already breaking across the coast. By the time the system had any information about what was happening, the dying was already over. The Itape event formalized a hard lesson for the international tsunami warning community. There is a class of tsunami events that the conventional warning system cannot reliably detect in advance. These events are produced by submarine landslides, volcanic flank collapses, and other gravitational failures, whose surface manifestation is a wave, but whose seismic signature is either absent or insufficient to trigger an automated response. The warning system catches up to the wave only after the wave has done its damage. For the central Bismarck Sea, the operational implication is direct. If a flank collapse were to occur on the central ridge, with debris volume even a quarter of the Ritter volume, the resulting tsunami could propagate to the nearest inhabited coastlines on Manus Island, the southern Bismarck Arc, or the broader Papua New Guinea coast within minutes. Whatever warning the Pacific Tsunami Warning Center is able to issue in that scenario would arrive after the wave. That is not a critique of the warning system. It is a structural feature of the kind of event we would be watching for. The frame that matters is the one in which the threat lives in the geometry of the volcanic edifice itself, and the warning is the eruption we are watching right now. The eruption is the warning. The Ritter debris fan at the bottom of the Bismarck Sea, 200 kilometers south, is the warning. The 1,600 dead at Itape are the warning. The worst case ceiling for what the central Bismarck Sea could become is bounded by Hunga Tonga. On the 15th of January, 2022, an underwater volcano in the South Pacific called Hunga Tonga Hunga Ha'apai produced what has now been confirmed as the largest volcanic eruption of the 21st century. Volcanic Explosivity Index 5.8, eruption column to 55 or 58 kilometers altitude, approximately 150 megatons of water vapor injected into the stratosphere. The pre-climax phase of Hunga Tonga, on the 14th of January, 2022, the day before the paroxysmal event, looked operationally similar to what the central Bismarck Sea is doing right now. A sustained explosive eruption from a submarine vent, an active seismic swarm, underwater to atmospheric ash transport. Within 24 hours of that pre-climax phase, Hunga Tonga had become a global event. The probability that the central Bismarck Sea volcano follows that trajectory is low. Most submarine eruptions with pre-climax phases like this do not escalate to paroxysmal events. The base rate for escalation is in the low single-digit % range over the duration of the eruption. The probability is low. It is not zero. And the difference between low and zero is what makes this an event everyone paying attention to the Western Pacific should be watching, even though the most likely outcome is that the eruption tapers and the system returns to dormancy. The watch window for the next 48 to 72 hours has two diagnostic signals. The first is the seismic catalog. If the magnitude floor stays at the magnitude 5.6 main shock from the 8th of May without new events at that level or above, the most likely interpretation is that the system is in a single intrusion phase that will taper. If new events at magnitude 5.5 or above appear, that indicates fresh magma is continuing to arrive and the eruption is in an early phase rather than at its peak. The second signal is the satellite imagery. The ash plume is the visible heartbeat of the eruption. As long as it sustains at 9,000 feet and spreads at 40 kilometers, the eruption is sustained at its current intensity. The watch window for the next week is whether secondary vents appear along the central Bismarck Sea ridge. New plumes from locations separated by kilometers from the current primary vent would indicate multi-vent activation. If new vents appear, the elevated risk window extends substantially beyond the duration of the current eruption. The most defensible reading right now is that the eruption is most likely a routine submarine arc event that will run at its current scale and then end. The elevated tsunami risk is real and meaningfully above baseline, but the probability of a flank collapse event in any individual day is low. The Hunga Tonga ceiling is real and bounded, but unlikely. The appropriate posture is informed attention, not panic. For coastal populations in the affected region, the practical operational response is awareness of the elevated risk, attention to local guidance from the Papua New Guinea National Disaster Center and the Pacific Tsunami Warning Center, and knowing the routes to higher ground in the way that coastal populations of historically tsunami-affected regions have always needed to know them. The eruption is the warning. The audience watching it is part of the warning system. The next several weeks are going to answer, in one direction or another, whether the central Bismarck Sea volcano stays at the scale it is at right now, or whether it does something we will remember for the next century.